Today we are doing 5.2, verifying trig identities. Last time this lesson follows 5.1, which was simplifying trig identities. So you're going to see a lot of the same techniques that we learned last time. But in this lesson we are verifying, which in essence means proof. So this is a formal proof. Although it's not like a two-column proof in geometry, it still has its own formatting and own rules that must be followed in order to complete the proof. Just as with any geometric proof, sometimes there may be more than one way to get to your answer. So as long as you're applying the rules correctly, then you should be okay. The rules that we're following, we're going to begin with the left or the right side of an identity, and we are going to prove the opposite side. We're never going to work with both sides at the same time. So I can start with the left and prove the right side, or I can start with the right side and prove the left side. We work vertically down the page, and we only work down that one side. So when you do your proof and the formal formatting of it, you're going to have your first statement, and then all the work will follow underneath that one side. You only work that side the entire proof. You can never switch back and forth. You will only have one equal sign per line, and you do have to have an equal sign per line. You may only make one type of identity change at a time. So like last time, we might have made a Pythagorean and a quotient identity replacement at the same time. Here you have to do one at a time. You have to demonstrate each of the specific things that you're doing. It does have an equal sign in your trig identities. You know, we have all those trig identities on the back side of our help sheet. They have an equal sign. However, you cannot do algebra steps when you're solving. You again must follow the same patterns that you did last time, replace with a known trig identity or an algebraic identity. Absolutely no mental math steps on this one. So you can't cross out like you could when you simplify. You can't just know something's happening. You've got to demonstrate that it's happening. So those are kind of the things there. We are going to be working through these 7 examples of proofs. Now in my notes I did write why I did what I did on the right hand side of the page, but that's not something you actually have to do in your proof. I just thought it might be helpful as you're reading through the examples. So here is an example of the difference between a problem that's a simplify and a problem that is a verify. So simplify is what we did in 5.1. So here's what we were simplifying. So I pulled off the numerator. I had a reciprocal identity here. I know these two things are going to cancel out and be 1 because anything divided by itself is 1. And so that left me with sine squared theta. So you can see just a couple of steps to get there. The proof, however, so now we're showing that this equals the other side, which is sine squared theta. So you can go right to left or left to right. I usually try to pick the side that has the most stuff to work with. Makes it easier. It's always easier to simplify things down. So you write down the side that you're going to begin with, whether it's the right side or the left side. And then you have your equal sign, and this is the first step of your proof right here. So I pulled my numerator off, and so I have that. Then I said, okay, I know this is a replacement identity because tan squared theta just means tan theta, tan theta. So that means sine squared theta over cosine squared theta times sine squared theta over cosine squared theta. So you get this. And you haven't done anything to the reciprocal identity here yet. So now I'm going to use my reciprocal identity, and I'm going to flip this upside down, and I get sine squared theta over cosine squared theta times sine squared theta times 1. So I'm right here. So then I'm going to rearrange because we know we can multiply in any order. Multiplication is commutative. So I rewrote it and moved the cosine squared theta over here because I know anything divided by itself is 1. And if we were simplifying like over here, we could just mark it out. But we have to demonstrate that's 1. So we need to show the reader that you have something divided by itself. So now that you know you can see it here, you can make the replacement here. And then you're left with sine squared theta times 1. So no mental math steps, no crossouts. And this is the end. So you can see here's where I started. Here's all the work I did to prove it, and here's where I ended. And then these two things for me would match up. So that's what we're doing today. So let's look at the first one. We are simplifying, not simplifying, we are verifying secant squared theta minus 1 over secant squared theta equals sine squared theta. So this one has the most stuff, so I'm going to prove it left to right. So I write down my first side, the one I'm going to prove is over here, and I do it this way because that way I can do the same style of proof whether I do left or right. So you always write down what it is you're going to prove. And then my first step was to separate this. So remember, if I have two separate things in the numerator, then I can say that that was two fractions that had a common denominator. So this is one technique. I could factor this, but factoring it to secant theta plus 1, secant theta minus 1 isn't going to help me get rid of the secant in the bottom. So although this is factorable, the factoring isn't going to help us right now. So what I did is I took the secant squared theta and put it over its denominator minus the 1 over its denominator. And so now I have two separate fractions. Well, handily, this is actually something divided by itself, so I don't have to regroup or reorganize. I can just say it's 1, and I still have 1 over secant squared theta. Now that I know that this is a reciprocal identity, I can replace it, and I get cosine squared theta, and I know that 1 minus cosine squared theta is a Pythagorean identity, which is sine squared theta. So I have now proved from this side, which was the left, to this side, which was the right. So this is what I meant. I just kind of wrote down in my notes what I was doing so you would know that. But if you were actually looking at your own formal proof, it would just look something like that. All right, moving on to question 2. And I'm giving you different techniques as we go through this, just like in the other sections that we've done. Just remember, some techniques could be interchanged with others in a problem. So it becomes imperative that you are very, very specific in the steps that you write, because I will have to read every line of your proof, and if I can't follow your thought process, that means you haven't demonstrated to me what you're thinking. Okay, so keep that in mind. So I looked at these two sides, obviously more stuff over here, so I'm going to prove from the left to the right. So here's where I started. So the first thing I have to do when I have two separate fractions is get them together, and I do that by finding a common denominator. So you could think about this as smiling. If you're in my class, you've heard me say that before. You know, basically all we're doing is getting a common denominator. So I multiplied this top and the bottom by 1 plus sine alpha, and this bottom and the top by 1 minus sine alpha. So that's what I'm doing right here. And I get my common denominator, and I have my new numerators, and now I can put them together over the common denominator. So once I get it up here, I mean, I can kind of look at that and go, hey, sine alpha minus sine alpha, that's just going to be 1, or 0, excuse me, they're going to be opposites. However, I need to show those opposites, so I need to rewrite the numerator. I can't just mark that out. So I pulled this one up here, and I pulled this sign back here. I just rewrote it because addition is commutative. And now I can see that I can do 1 plus 1 is 2, and sine alpha minus sine alpha is 0. And then 2 plus 0 is 0. So all the way down to here from our steps in our proof is using that algebra identity. So now that we're down here, I again kind of hold off till you get toward the end of a proof to simplify this, because you might miss a factor along the way, and then you would have to create extra steps to get back to it. So now that I'm here, I'm going to go ahead and FOIL this together. So I need to show that I FOILed that right there. It can't just miraculously go from here to here. I know that's what's happening, but in a proof I have to show that's what's happening. So here is where I FOILed it out and got down to here. So now I know that the bottom is an identity. It's a Pythagorean identity. So I replace that and then pull the numerator off. Once I pull the numerator off, I have a reciprocal identity, so I can replace it. And then I have 2 secant squared alpha. And that's what I was trying to prove. That's what this side of the proof was. So again, I'm just doing a kind of some examples here to show you and help you work through so you have some different strategies. Let me get on to the next page here. All right, so on this one, number 3, we are proving tan theta plus cotan theta equals secant theta cosecant theta. I tend to go with this one because I have two separate things to work with. This is technically all one term. So I am going to prove this left to right. So I write down what I'm proving. And the first step is I'm going to use my quotient identity. So I change that to quotient and that to quotient because I'm trying to figure out a way to get them together. Remember, I'm going from 2 pieces here to 1 piece here. So this has to combine. So tangent is sine theta over cosine theta, and cotan is cosine theta over sine theta. So now we're getting a common denominator. So I multiply the bottom and the top of this side by sine theta, and then I multiply the bottom and the top of this side by cosine theta. So now I have this numerator and I have this numerator all together over the common denominator. So I know multiplying together, sine theta times sine theta is sine squared theta, cosine theta is cosine squared theta, all over my denominator. And I know that this is the Pythagorean identity, so that's 1. And I still have this in the denominator. And I know that if I multiply these two together, I had to be able to multiply the numerator together and get 1. So that means the numerators were 1 and 1. And so I can spread this back into my two products. And because these are both reciprocal identities, then I can make that replacement here and that replacement here. If they're the same kind of identity, you can make double replacements in the same process like that. If they're different, if one was a Pythagorean and one was a reciprocal, each one would need its own step in the proof. And so now you can see here is the side I started with on the left. Down here is the side I started with on the right. Everything is worked underneath that side. Everything has an equal sign. So there is a definite formal process to this proof. All right, moving on to 4. So on 4, we're doing secant y plus tan y equals cosecant y over 1 minus sine y. So there's two separate pieces here, so that's why I'm proving left to right. So I write down what it is I'm proving. I'm doing secant y plus tan y. And then I am going to use a reciprocal and a quotient at the same time. Those are both similar in style, so you can use those in the same step. Okay? So then I'm going to kind of do a little, this is a technique called multiplying by a factor of 1. I'm trying to manipulate this equation a little bit because I can see that I have a 1 plus sign up here, but remember what I'm looking for in the end is 1 minus sine y. So I'm multiplying it by a factor of 1. And when we do that, this is going to distribute, this is going to multiply. So in the top, I have to FOIL, which gives me all of this. And then multiply the bottom, so I get this. Okay, so it was a way to kind of force that down in the bottom. That's the technique, multiply by a factor of 1. Okay, so I have a negative and a positive, so I know that cancels to be that 0 right there. I have my 1, and I have sine squared y. And then I know that the 0 will go away, so now I have 1 minus sine squared y. And there's a couple of ways to go about this. If I factor, because that's a difference of squares, then this is going to cancel, right? But remember, I wanted that to be there in the end. So I don't want to factor cancel here. What I want to do is use an identity. So I'm going to replace this with its Pythagorean identity right here. And then on top, remember that's cosine y, so that's what I have here so that I can show something divided by itself as 1 and leave me with cosine y over 1 minus sine y. So you can see right here I had some decisions to make. I had to decide, do I want to factor cancel? What's that going to get me in the end? Is that going to get me where I want to go? And it wouldn't. So then I said, okay, well, what about the identity? So you do have to think and make some decisions as you go through this process. So when I get down here, I have my 1 from here. I have my cosine y, 1 minus sine y. 1 times anything is that. And that's what I was trying to prove. So look at the form again. Here's where I started. Here's the first step. Here's each step underneath, making one replacement at a time, one equal sign per line, showing everything, not doing any mental math. And then I get down to the right side. Okay, so that's that big formal proof we've been talking about. All right, the next kind of proofs I want to talk about because it seems like students want to just jump straight in to using quotient and reciprocal identities. A proof like this should not take more than 3, 4, 5 lines. If it does, your teacher is probably going to quit grading. Okay, because that means you didn't understand how to do this kind of proof. So we're going to do 3 of these factor proofs and pay special attention. I would expect it to be on the test. And again, not going to, I have students that will do a proof like this, like 10, 15 steps. All right, and that's not what it should be. It should be 3, 4, or 5, so you have to pay attention. All right, so these I'm doing right to left because this is the bigger side. So notice I write the side down I'm working with just like normal. And then I am going to factor. So see how it's connected with the minus, and we have a set of terms here and a term, or it's not a set, a term here and a term here. Each of them have a common factor of tan squared, so I'm going to factor that out. And that's factoring out the GCF. That's the technique here. So once I factor out the GCF, and I want to take out the greatest common factor, I don't want to spend 5 lines taking one thing out at a time. The greatest common factor is the technique. That leaves me with sine squared x minus 1, because remember when I factor out tan squared x, that means I'm dividing it from this side and I'm dividing it out from that side. So I get secant squared x left here because I would have tan squared x divided by tan squared x, which is 1. I would have tan squared x divided by tan squared x, which is 1 right here. So once I've done that, then you should see that you have an identity right here, which is tan squared theta, and tan squared theta times tan squared theta is tan to the 4th theta. Okay, there should not be any reciprocal identity replacements, quotient identity replacements on a proof like this. So keep that in mind. All right, let's do B. Okay, on B we have sine cubed y, cosine 4y, and over here we have cosine 4y minus cosine to the 6y sine y. So again, I'm going to prove right to left because there's way more stuff on this side than this side. So that's the first step I write down. Then the first step that I'm doing in my proofs, this is in parentheses right here, so I'm going to pull out a GCF from these two things. So the GCF is cosine to the 4th y, greatest common factor, not a common factor. The technique is greatest common factor. So once I divide that cosine 4y out from here and here, I'm left with 1 minus cosine squared y times the sine y that I haven't done anything with. Inside is an identity. So I make an identity replacement with a Pythagorean identity. Pythagorean identities happen, remember, when they're powers of 2, not singles. So I have sine squared theta, and I can combine together. So I get cosine 4y, and I get sine squared y times sine y, which is sine cubed y. And then just the last step is putting it in the right order, so you actually have the same order as in your proof. Okay? So C. All right, another one. So you can see lots of high powers in these. That's where this kind of comes in. So I have a secant squared x times cotan x plus cotan cubed x. That's where I'm starting, so that's the step I write down. Then my first step is going to be to factor out. So this right here, I factored out a cotan x. And then I have 1 plus cotan squared x. And so I have an identity, so I make that replacement. And then these two things can multiply together, so I move them together because remember I have to show it. And so cosecant squared x times cosecant squared x is cosecant 4x and cotan x, which is what I was trying to prove. Okay, so when you have a higher power proof like this and you're trying to get down to one side to the other, do not use quotient or reciprocal identities. This is just going to cause a lot of extra stuff that, to be honest, probably is not going to be graded. Because giving you this kind of proof is supposed to be you demonstrating you know how to do this kind of proof, not just spinning your wheels for an entire page trying to find something that just happens to work. So please, 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 please pay attention to number 5 and make sure you can handle problems like that because they will be on the test. So as we move into more complicated ones, they do get a little bit longer, but don't panic, just take a step at a time. So I look at my two signs here and I decided I would prove this left to right, so I write down my left side because that's how I'm proving it. Then remember the first step here is the first step of my proof, which was pulling the two fractions back apart that were multiplied. We did this technique earlier. Then I used reciprocal identities and got cosine x times cotan x. And then I used a quotient identity for cotan. Remember that's cosine x sine x. Cosine x over sine x. And so now I'm going to need to put these together, so I need to show that this is a fraction, so I put it over 1. And then I can multiply the numerators and multiply the denominators. So I get here. All right, so this is an identity. So I replace it with my Pythagorean identity. Now I have two numerators over a common denominator, so I can split the fractions back apart. So there's the 1 that was here, and the minus is the operation, and the sign squared is over here. And I know I have things that are going to cancel here, but remember, even though I know it, I have to show it. So sine x times sine x over sine x times 1. So now you can see the 1 right here. So that's the one that's going to cancel down to 1. And you're left with times sine x. Okay, so now we can finish this thing up. We're really close. 1 over sine x is a reciprocal identity, which gives us cosecant x. And then 1 times sine just gives us that minus sine x. So we've proved it. Again, here's where I started. Here's the first step. Here's all the steps that run down the page, all the way down to my final proof here. All right, moving on. We only have 2 left, guys. 7. So we're verifying again, which means proving. And I have cosine x minus cosine x over 1 minus tan x equals sine x cosine x, sine x minus cosine x on the bottom. So because this is multiple pieces, that's why I choose to go left to right. It's not saying you couldn't go right to left. It's going to be more work going the other way around. So when I have multiple pieces, it's much easier to bring them together. So here's the first one, because this is the left side that I'm proving. Here is the first step of my proof. So I have cosine over 1. So I just changed it to fractions because I'm dealing with 2 fractions. And then I want to get my common denominator. So I'm multiplying the bottom and the top by 1 plus tan x. And on this side now I have cosine x, 1 plus tan x. I have the cosine x over here, and I have my common denominator there. So now I'm going to distribute through. So I can do cosine x minus cosine x tan x minus cosine x all over 1 minus tan x. So now we're going to replace, because I need to kind of separate things out. So since this is a product in here, and I know that tangent is sine over cosine, that cosine on the bottom would have something to do with this cosine on the top. So I'm going to use my quotient identity and make that replacement right here. So now I can put these two things together as a product. And notice when I put my product together, I'm putting the cosine over the cosine, so I can just show that right there, and sine over 1. So cosine over cosine is 1. Sine x over 1 is sine x. Now, as I'm looking at the proof here, I know that the 1 times sine is going to give me sine, but notice that you've got this cosine here and this negative cosine there. Those are opposites, so we want to move the opposites together so that we can show that they eliminate. So I'm going to pull this negative cosine up here. Be sure you take the negative with it. And I'm going to pull this 1 times sine x, which is minus sine x, right back there. So now I know that cosine x minus cosine x is 0, and minus sine x on top. So minus sine x on top and 1 minus tan x on bottom. I need to get this together as a single fraction, so I need to do something with the bottom. So the way I'm going to put that together is I'm going to make them a fraction so that I can combine them. So I'm going to rewrite the fraction at 1 as a fraction that equals 1. So, okay, going to be something over itself. Since tangent is sine over cosine, then the 1 is going to be cosine x over cosine x, because I want these to be able to combine together easily. So after I had my identity over here, it became easy to see what is the unit of 1 that I want to change that 1 to, the fraction I want it to be. If I change it to cosine x over cosine x, I have a common denominator. So now I have in the numerator cosine x minus sine x over cosine x. Okay, so as that sinks in, I'm going to move on to the next page. So when I went from here to here, right, this means this divided by this, and so I know that when I divide by a fraction, that's the same thing as multiplying by the reciprocal. So that's what I did. I have negative sine x over 1, and this was cosine x minus sine x, so that's going to be in the bottom. The cosine x is going to be on top, and now it's a multiplication problem. Okay, so we're here with the multiplication. So we can put them together, multiply the top times the top and the bottom times the bottom. So I get negative sine x cosine x over cosine x minus sine x. So as I'm looking this, I know it seems like an awful long time since we started at the top of this, but notice up here I have a sine x minus cosine x in the bottom. That's what I'm trying to prove. Don't lose sight of what you're trying to prove. So I have the cosine x minus sine x in the bottom. So, okay, that's good. The only difference is the stuff that's left, right? And here's the thing. I have this minus here, but my numerator in my final step that I'm trying to prove is positive. So I'm going to factor out, or think of that as a -1. And we know that we can put a negative in the numerator, the denominator, or out in front of the fraction. So I'm going to move it to the bottom. And so I showed the -1 here, and I showed now that it's in the bottom. And the reason that's in the bottom then is that's going to flip those signs, and it's going to make me have a negative cosine instead of a positive cosine. I need to change these cosine signs on the cosine and sine right here. So I bring it down to the bottom and distribute it through, and so now I have a negative cosine x plus sine x, and I have sine x cosine x on top. So to get it in my final form that I was trying to prove, I just need to rearrange these two things in the denominator so it's sine x minus cosine x. And remember, that was the proof that we were trying to prove right here. We started with this side and we ended with this side. So you kind of see how as I'm thinking through the proof, I'm looking at, okay, well, what needs to be negative in the end? How am I going to do that? All of those things have to be part of your thought process. And so here's kind of the factor, or the technique here is moving that negative sign to the bottom of the fraction and distributing it through. That lets us rewrite and change things without changing the value of the problem. So these are the problems that are in our notes for today. The next thing would be the homework for these problems. Now here's the thing, guys. If you want to get good at proofs and you want to be able to do this efficiently on the test and not run out of time, you got to practice them, okay? Because the more you do of them, the more you see patterns and you recognize, oh, I need to do this. Oh, I need to do this. The fewer you do, the harder that's going to be for you. So my advice is work on some problems. When you're working your homework, if you have questions, make a note and ask me. If you're one of my students, ask your teacher if you are from a different class, and get the help that you need, because proofs are kind of like proving is kind of like a puzzle. In algebra proofs, you don't have to give a reason why you're doing it, like I did down the side of the page over here. That was just for your benefit. But that's different from geometry proofs. So as soon as you start recognizing the patterns, then you don't have to worry about it. It's not like you're having to name them. So just know, as I go down the page beside my notes and I'm giving you reasons why, that's just me kind of giving you some guidelines. It's not necessarily required, but hopefully you'll start recognizing those patterns. So again, follow the rules. Make sure you're doing legitimate things. Make sure that you remember the difference between a simplifying problem like this side and a proving problem like this side. Pay special attention to your form and pay special attention to making sure it's organized. Because as I'm reading a proof, if something is confusing to me, then you haven't demonstrated the math that's going on, and that means you haven't proved anything. All right, guys, so I will see you next time, and we will talk more about verifying and simplifying. And tonight's homework, be sure you're practicing verifying identities. There is a lot of resources for you. If you remember calcchat.com, you can go to Chapter 5, Section 2. You can go to any of the odd problems that it shows you, and it will give you a solution. So if you want more practice, go into your 5.2 in your calcchat.com, and then, you know, it will give you a solution to help you so you can get better at it. All right. Bye, guys.